A 2 kilogram block is attached to an uncompressed spring with a spring constant of K equals 200 newtons per meter. The block is initially at rest on a frictionless surface, and the spring is attached to a wall. And in an experiment, there's a 0.1 kilogram ball of clay thrown at the block, which is moving with a speed v of 63 meters per second. Part A, calculate the speed of the clay and the block immediately after the clay sticks to the block, but before the spring compresses. So this is a combination of conservation of momentum, because there's a collision between the clay and the block, combined with conservation of energy, as this block is moving, which is kinetic energy, to compress the spring. So it's converting kinetic energy into elastic energy. So we've got to look at the two parts of the problem separately. The conservation of momentum, which will result in a final velocity, a v final, of the block with the clay attached to it. And that final velocity becomes the initial velocity for the conservation of energy part of the problem. So, calculate the speed of the clay in the block immediately after the clay sticks to the block, but before the spring compresses. So we're looking at just the conservation of momentum part. So we want to set up the M1 V1 initial plus M2 V2 initial, and since they are stuck together, we're going to use the conservation momentum equation that has M1 plus M2 stuck together with a combined final velocity. So let's make M1 represent the clay ball and M2 represent the block. And since the block is initially not moving, we can say that the initial momentum of the block is 0. And now we can just plug in, or at least solve for VF, and then plug in the rest of the numbers. So I'm going to divide both sides of this equation by M1 plus M2. That will give me the VF by itself. When you plug in M1 initial, when you plug in M1 right here, that's the mass of the clay, which is 0.1, times its velocity, 63, divided by 0.1 plus the mass of the block is 2. So divided by 2.1, you should get the answer of 3 meters per second. Okay, now that we know the block with the clay attached to it is moving at 3 meters per second, that's basically kinetic energy of the block clay system, which is going to be converted into the elastic energy of that spring as it compresses the spring. So this is where we want to set up now for part B, the conservation of energy. Ki plus Ui is equal to Kf plus Uf. Since there's no change in height in this problem, it's all taking place on one level, we have no gravitational energy, but we are dealing with elastic energy. So we're looking at this initial velocity right here, which is the final velocity that we just solved for. That initial velocity is what's going to be plugged into that initial kinetic energy. So don't say the initial kinetic energy is 0 because you think the block's not moving. Remember, this is immediately after the clay hits it. That's the initial kinetic energy we're talking about. And at that point, the block clay system is moving at 3 meters per second, which you calculated in part A. But initially, the spring is not compressed. So we can say that U initial is 0 because there's no elastic energy. And then when the spring is fully compressed, it is going to be momentarily stopped, so the final kinetic energy at full compression is 0, but because the spring is compressed at that point, it does have elastic energy. So if we plug in the formulas, 1/2 m v initial squared is equal to 1/2 k x final squared. What does this m in this formula represent? Is it the mass of the block or the mass of the clay? Well, remember, the two things were stuck together immediately after the collision, so that M is actually the joint mass of the clay block system, which is 2.1. So we can just take this whole equation now. We know the M, we know the initial speed, which we just solved for, was 3 meters per second. We know the K is 200, and we are solving for the X, which is how much the spring compresses by. You can make this equation a little bit simpler by canceling out the 1/2 on both sides. And when you solve for X, it is going to be given in meters. So the answer is that you should get in your calculator is about 0.307 meters, which I then converted into centimeters to put on the to put as the answer to this question. Part C, calculate the mechanical energy of the system before the clay hits the block. So mechanical energy is just all the kinetic and elastic energies that exist. So before the clay hits the block, there's no elastic energy because the spring is not compressed, so we only have kinetic energy. So I'll actually start and just call this, because it's the mechanical energy we're looking for, the E initial is just equal to the kinetic energy of the clay, the initial kinetic energy, which is 1/2 m v initial squared. That's 1/2 times 0.1 times 63 squared, and that's where the answer of 198 joules comes from. In part D, calculate the mechanical energy of the system when the spring is at maximum compression. So the final mechanical energy of the whole entire process is only going to be elastic energy, because when the spring is at maximum compression, there's no more motion, there's no more movement in the system. So it's just going to be 1/2 k x squared. So 1/2 times 200 times this value that you got for x, put it back as meters, not in centimeters. So 0.307 squared, and that's where the answer of 9.4 joules comes from. And now if we compare those two answers, we can see that initially the system had 198 joules of energy, and at the end the system only had 9.4 joules of energy. So we want to explain why the mechanical energy of the system is not conserved. And this should be a pretty obvious answer, because if you go back to the beginning, the type of collision that we had was a perfectly inelastic collision because the two items stuck together. And in a perfectly inelastic collision, the maximum amount of kinetic energy is lost. So you're going to lose a lot of energy just during that part of the collision, and all the energy was lost going from the initial to the final values. Part F, indicate whether the collision between the clay and the block is elastic or inelastic. Justify the answer without calculations. And we just said that since the two items stuck together, it makes it an inelastic collision, because when two items stick together, that is perfectly inelastic, which is just a subcategory of an inelastic collision. How would you justify the answer to part G without using calculations? With using calculations. In part G, you want to calculate the kinetic energy before, which is 198 joules, and then you want to calculate the kinetic energy immediately after the collision, which, if you go through the process, you should end up getting the same answer right here, because that is the elastic energy when it's fully compressed, but that should be the same as the kinetic energy right when the system starts moving, since energy was conserved, at least in that part of the system. So because the kinetic energy before the collision is not the same as the kinetic energy after the collision, we can say that it's an inelastic collision.